Hey everyone, in this video, let's take a look at question 139, word break on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, we're given a string s and a dictionary of strings word dict, and we want to return true if s can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in the segmentation. Okay, so let's take a look at how this forms here. Take a look at this example that we have here. Okay, so basically we're given the word Leetcode and the words are leet and then code. We can notice that we can actually separate this as something like this. And so this is a word and this is a word. So we return true. It looks like we're just returning true or false basically to see if like we can form the words. In here, we can do apple, pen, and then we can actually reuse apple. So that's why we return true. In this one, it looks like we can return false because cats and dog, right? So it basically won't work. Here, even if we have like something like this, we don't have the A and N, and so it don't work. And also, maybe something like this, cat, sand, dog, well, sand doesn't exist, so we actually can't form this. So this doesn't work. So how might we go about doing this problem here that we have? So let's take a look here. Let's say we have the word, right? Like we have the string and we have the word dictionary here. Well, first of all, I know that like I'm going to keep checking to see whether a certain string is in this word dictionary. So it might actually make sense to convert this into a set. So maybe let me just do set predict. So this will be like a O of n time lookup. So which is better than a list here. So that's like one thing we notice right off the bat. Now what's another thing we notice? Well, I know that I have to go through this like this list here, right? I have to go through this list and I basically have to consider like the word that I'm forming so far. So maybe let's say we have the word Leetcode here. And maybe I can start off at like I here, and then I can see whether I can form like, I guess here there's nothing really here, right? So we can check if we can form like the word L, right? Can we form the word L? We can't. So let's just maybe advance this, and we'll keep advancing this until we arrive at the T, right? And so now if we can form the word leet, then what do I want to know? Well, then I want to know if I can form like any of the words on the right hand side of the string. If I can form like the word code here, for example. Now, how can I maybe do that? Well, notice that if I can form the word code, right? Maybe this code over here is like actually broken down into something like CO and then D here, right? Maybe it's something like this. So if I want to figure out like whether I can form the word code, this in itself is like its own problem, right? It's its own sub problem. So if you kind of think about it, we can just do this in another type of call, maybe a recursive call in which we pass in the word code over here. And so what can I do? Well, if I know that up till this point I was able to form the word leet, and then I do a recursive call, and then I can also form the word code over here somehow, I don't know how, but I can form the word code. Well, then I know that I can form the word leet, and then I can also form the word that appears after my current index. And so if that's the case, then I can arrive at my solution, which is true in this case. So maybe that's like a way in which we can start off this using a recursive type approach. So let's kind of take a look at how that might work out, how we might be able to go ahead and do something like that. And notice here actually that like if for example, let's suppose for example that we had also another word where it was just like LE, right? We just had the word LE. So in this case, when you arrive at LE, we'll try to see if we can somehow form this entire thing. And notice that we're actually not able to, right? Like we'll try to maybe do, we'll try to start off our J index over here, and we'll try to see if we can form E. We can't. Can we form ET? We can't. So then we'll see if we can form like maybe ET code. We can't. So what do? Well, then we return, and then we move this I pointer ahead. And so that's how we might go about like doing the solution. So let's take a look at how we can do the recursive case and what do I have to worry about here. So our unique 111. Okay, so there's no like empty case, so we don't have to worry about that. Okay, so what can we do? Well, let's maybe go ahead and do a recursive call, and we can just make a recursive call return true if you know, like this entire word can be formed. So what are some of the things I need to pass into my recursive call? Well, I need to pass in the string itself. I need to pass in the word dictionary. I also need to kind of pass in like the index, right? Because if I'm considering like this leet over here, then when I do my next recursive call, I want to consider the code. So in that sense, I also kind of want to pass in like my index over here. And I think that should be all, right? I think that should be all. Okay, so all right. So how do we know if I've like essentially formed my word, right? Like how do I know? Well, let's think of like a simple case, right? Let's say my word is just leet, right? Let's say my word is just leet. So I will start off over here, I will be like my index, right? So maybe we can have like something like for I in range and then index to length of s, and then like we'll pass something here. What is our base case? Well, our base case, if you think about like, let's suppose that I'm here. Until this point, I can form the word leet. I can form the word leet, right? So if I can form the word leet, I want to see if I can form like anything that's over here. Assume this is like an empty space, right? So if you think about it, if my index ever reaches like out of bounds, then I know that I've already formed the entire words up till this point. So in this case, I can check like if index is equal to the length of s, well then I can just return true here, right? Because it means that I've already formed all of this. So now I'm just checking to see if I can like form like an empty string here. So obviously I can, right? So that's why it's like a true here. Okay. But now what? Well, now let's go back. Let's go back to something like here, to something like Leetcode. Well, now index and I, they both start off over here. Okay, index and I both start off over here. And so now we want to see like what is the current word I can form based off of like this current index. It would just be L, right? So I can do something like word. What would my word be? Well, my word, it would be S, and then what would it be? Well, it would be 0 to, I guess, I plus 1, right? In the beginning, I is 0. So I is 0, 1. Let me just write this. Okay, so something like that. So my word here would be 0 to the second index, but like really, if you think about it, like that's like just forms this L over here. So now we have our word, and then what I want to check, so I can check if word in word dict, or I guess if word in words, if this is the case, and what, and so if my word is currently in word, so let's say I was all the way over here, right? So if this is in word, and I can form this word over here, and self.helper s words, and what should my index be? Well, it would be I plus 1, right? It would be this word, I plus 1. If this is the case, then I can return true. I will try this for every single case, and if I ever exit out of this, then I will return false. So we actually have I just noticed we have a bug here. And so what is the word? What is the bug? Well, if you think about this, like, notice how when we're creating the word over here, we're actually starting off from index 0, right? But that's actually not correct, because when we do a recursive call, like let's suppose like our I goes over here, well then my word now is just C, right? It shouldn't be this entire thing. So actually my word, the starting index should be just index here, and then it should go from I plus 1. So that's why we'll just form the C here. And so that's basically how we can start off by this. So let's take a look at what we want to pass in. So we can pass in S, we can pass in words, and we can pass in 0 as our starting index. So let's take a look at this and see if it passes. So it does. Let's go ahead and submit it. We should hopefully see that it passes, but maybe it's going to take too long. So we can see how we can memorize this one to make it faster. So let's go ahead and do that approach once this TLEs. Okay, so I'm just assuming it's okay. So TLE is perfect. So now we can do memoization, right? So in memoization, what do we have? Well, we have a dictionary in which we cache our results, and I'll pass in my memo to these two information here. Okay, so what do I need to pass in? Well, if you think about it, the only thing that's really changing is this index over here, right? All of this remains the same. All of this remains the same. So we only need to cache our index. So what I can do is I can actually do something like, let's see. Okay, so every time like we're returning true or false, we want to cache that information. So here I can do like memo at index is equal to false, right? Here I can do something like memo at index is equal to true, and I'll return memo at index. And maybe here I can also just return memo at index. And then I need to check this. So I can check if index in memo, then I can return memo at index. And this case, I think we don't really need to check because it's just a base case here. But let's take a look and try this solution now. So I'll go ahead and copy this actually, see if it works. Let me try this out. Okay, so it works. Let's go ahead and submit it. And it also works perfect. Okay, so this is another working solution. Now, we can actually make this a little bit better, and we can do dynamic programming. So we do recursion, then we do memoization, and then in the end, we do dynamic programming to basically stop doing recursion altogether. So what do I need in dynamic programming? Well, in DP, I need an array that will basically cache my recursive results. So we can find out my array should be, what should be the items inside, and what should the size of the array be, simply by looking at the memoization here. So I can see that in memo here, first of all, what am I returning? Well, it looks like it's storing true or false. So I know my DP array has to store, I guess, false initially for everything. Now, what should the size of the DP array be? Well, if you take a look at this, DP array, or the memo here, is actually just encoding the indice, right? And the indice starts off as 0, and it can go all the way to the length of the string here. So really what it makes sense is my DP array be length of the string in total size, actually plus 1. Why the plus 1? Well, because at the very end, when DP is equal to this length of s, right? So when DP, when you're looking at this last indice here, the value should be true. When the index is the last value, it should be true. So now we've created our DP array, and so all we need to do now is go ahead and we could recurse, or we could go through our for loop here to fill out the DP array. Now, let's just take a moment to understand what exactly the DP array is saying here. Let's assume that I have the string Leetcode, okay, and here I have my indices 0, 1, 2, 3, 4, 5, 6, and then looks like I also have like this 8th indice here, or the empty string here. So what do? Initially, all of this is false, and then this one we set equal to true. Okay, so we know that. Now the DP array here essentially encodes the same thing that the memo encodes in the recursive call. So for example, let's suppose here that this value here was equal to true. Well, what this would mean is that from this specific indice here, I was able to find a word such that I was able to word break this word and then onward. So I was able to word break code and then onwards as well. It's possible that maybe this entire thing is also a word. But basically what I know is that from this index over here, I was able to form a word, potentially, and word break to the rest of the list. If maybe I have something here, if this is true, what does it mean? Well, it means that I was able to essentially word break from this index onwards all the way to the end. If you think about it here, what I'm actually returning is dp of 0, right? dp of 0 will give me my result. I can't return dp of -1 because this is just obviously set as true. So I really want to return dp of 0. And if you really think about this, it makes sense because take a look at what we're doing here. Here, we are looking at self.helper and then I plus 1, right? I plus 1. Now, normally, like when you're doing your DP, you don't have access to I plus 1, right? Because if I'm doing my DP from left to right, then, for example, if my I is over here, I don't know what this value is over here. I don't know. This is why we did the recursive call, to figure it out. But if I'm doing DP, I don't actually have access to the next value. I only have access to like the previous values. Or maybe I need to loop in an intelligent way such that I have access to the next values, as shown over here. So what can we do? Well, maybe instead of just looping normally, maybe instead of looping from left to right, how about we loop from right to left? And we update the DP array in that sense. And so at the very end, if we go ahead and we update this, then we know that starting from here, I was able to form a word or word break all the way that encompasses the entire string. Let's maybe go ahead and start with that. So how can I do that? Well, first of all, let's just understand, again, what DP means. So for example, if DP at I is equal to true, it means I was able to word break from S at I and then onwards, right? Onwards. Here's the key thing here. So for example, if it's 0, then I was able to word break from here and onwards. It's the same exact thing that we understood from here. All right, so let's go ahead and loop through our DP array so we can consider all sorts of indices. In recursion, we already kind of did that, but in DP, we have to consider all sorts of indices. So what can we do? Well, we have to start off at the end, right? Because we're recursing, or we're looping from right to left. So I can do for I in range, I will go from length of DP -1, and I will do -1, -1. So I will go all the way from 8 to 0. And what do I need to do? Well, now what I need to do is essentially look to see like the set of words that I can create, right? The sets of words that I can create. So for example, if my I starts off over here, I need to know like whether I can form the word code, and then maybe I can look at DP at I to see if I can form the next letter. So what can I do? Well, maybe how about we have another pointer, let's call it J, and J will start off not at I, but I -1. So we can do for J in range, I -1, and then also go to the front, and then we can form a word, right? We can form a word, which is J to I. So it's similar to what we're doing here, but just in an iterative fashion. which is s at j to I. And now what? Well, now we need to check if word in words, so if this is a valid word, which is exactly what we're doing here. So if that is the case, and what? And I was able to form a word break after this word here. So that's encoded by dp at I. And dp at I, so if this is the case, so if I was to form this word here, and I was able to form dp at I, which is essentially our I plus 1 in this index, in this way, you can think of it as I plus 1, simply because of like how this works here. If this is the case, then what? Well, then I'm essentially able to know that dp at j here will essentially equal true. This value here will be equal true. And so that's what we did here. So now this is essentially the word break algorithm. So let's go ahead and run this and go ahead and submit it. And we can see where we arrive at the answer. Now I think we can actually make this look almost exactly like this. So for one, I think here, since we already accessed this dp at length of s, then I don't really need to look at -1, right? I can look at -2, because -1 we already kind of handled if you think about it, right? What else? Well, if that's the case, then I would start off over here, right? I would start off over here. And so in order for j to take this entire word like code, it would have to be j to I plus 1. And then here again, I would look at dp at I plus 1. And I think if we did that, it would look almost exactly the same as what we had here. And so we can go ahead and submit that. And okay, so we run into some edge cases, I guess. Yeah, you might run into that. Let's see what I did incorrectly here. So expected is true. So initially we had something like a, and then the empty string, and then 0, and then 1. And so this value is initially equal to false. This value is initially equal to true. So if this is the case, then what do we have? Then we start off I over here, and then it looks like actually, yeah, so it looks like here j would be like out of bounds, right? So in that case, like if we had like one letter, it might be a little bit tricky to handle. So yeah, that might be a little bit hard in this case. Okay, so if that's the case, what if we start off j exactly where I started off, and then see if this is somehow valid, if we can form something like this. And if we still can't, then I will go ahead and, okay, so it looks like this is also valid. So if you just consider the same indice, then it also works. But I just think that it doesn't really make sense. Like we should start off j like one more behind. But yeah, that's just personal preference. But anyways, that's how you do this problem word break. Just for the time and space, just so we have it, the time here, it looks like we're looping through the for loop here and then looping through the indice here. So you can kind of think of it as like an n squared type algorithm. And then for the space, it would just be just the length of the string, so O of n.